Now we're going to go on to the second type of chi-square test, chi-square a posteriori. And here we will look at parasite infections in trout in 2 lakes. So imagine we capture a total of 111 fish. 38 in Lake A and 73 in Lake B. And we count how many fish are infected with the parasite. In total, 57 fish are infected and 54 are not. But the frequency of infected fish might be different between the 2 lakes. We put all our observed values in a so-called contingency table. And the question we ask is the frequency of infected fish the same in Lake A and B? And we often try to put the null hypothesis in terms of dependence or independence. For example, the frequency of parasitized fish is independent of lake, and the alternative hypothesis, the frequency of parasitized fish is dependent on lake. Or we could also express it like this. The probability of finding a parasitized fish in Lake A is the same as the probability of finding a parasitized fish in Lake B. Here we will again use a chi-square test to test our null hypothesis. But we don't have any theoretically expected frequencies of how many fish that will be infected with a parasite. This is a chi-square a posteriori. We only wonder if the frequencies are the same in the different lakes, if the rows and the columns in the contingency table are independent of one another. However, we still need expected values to put in our equation, and these are the frequencies we would expect if our null hypothesis was true. And to get these frequencies, we use our marginal totals. And you can think of it like this. If the frequency of parasites were independent of lake, and we had caught a total of 57 fish with parasites and 38 fish in Lake A, the probability of a fish ending up in this position is the joint probability of a fish being infected with a parasite and coming from Lake A. And to get an absolute frequency, we also have to multiply by the total number of fish we have. So if the null hypothesis is true, the frequency of parasitized fish that we would expect to find in Lake A would be 19.51. In a simple contingency table like this, we only need to calculate this one value. Using the marginal totals, we easily get the other values. If we have 19.51 here, we need to have 37.49 parasitized fish in Lake B. These two numbers have to equal 57. And similarly, in this position, we have 38 minus 19.51, which is 18.49. And here, 73 minus 37.49, which is 35.51. And now we have all the numbers we need to get our chi-square statistic. The equation looks like this. So for each position, we have our observed value minus the expected values squared and divided by our expected value, and the same for each of these positions. And we end up with a chi-square statistic of 6.796. We also need to figure out our degrees of freedom. And in a contingency table, our degrees of freedom are the number of columns minus 1 times the number of rows minus 1. We have 2 columns and 2 rows, so we end up with 1 degree of freedom. Now we look in our chi-square table at 1 degree of freedom, and we find our critical chi-square value for 5%, which is 33.84. And our chi-square value is higher than this, which means that we have a significant p-value. In fact, our chi-square value is higher than the chi-square value for 1%, so our p-value will be lower than 1%. And this leads us to reject our null hypothesis and accept our alternative hypothesis. The frequency of parasitized fish is dependent on lake, or the frequency of parasitized fish is not the same in lake A and B.